we want to find the moment arm, our perpendicular or the lever arm, and the component of force, which is perpendicular to the body, for each of the following forces. Okay, let's start with this one first, and let's find the moment arm first. So for the moment arm, it says take the pivot at the top of the post. So here's our pivot. Next, we have to remember, what do we mean by moment arm? Moment arm is the distance between the pivot and the line of action. So for our line of action, we take our force and we extend it. So we just draw a line that goes along with that force. We draw it as long as we wish. Now we have to connect this line to the pivot point, and they have to connect at a right angle. So you see that my ruler is perpendicular to my line of action. I move it back and forth till I hit the pivot. So now I know if I draw a line from here to here, I'm going to get a right angle here. That makes this my moment arm, our perpendicular. Let's see, how are we going to find our perpendicular? Well, we know that the length of the post, we might call that R, is equal to 4 meters. That's from here to here. And the angle is 60 degrees relative to the horizontal. So if we look at our triangle and we think about trig, this is the hypotenuse, this is the opposite. So our perpendicular equals R times the sine of 60 degrees. So 4 meters times sine 60 degrees. Put that through the calculator, and what do we get? 4 times sine of 60 equals 3.46 meters. So for this problem, the moment arm is 3.46 meters. Okay, next let's find the perpendicular component of the force. Let's go to a new diagram now, because this one's a little bit messy. So our force is right here. We want to break this into components that are perpendicular to the post and parallel to the post. So a line that's perpendicular to the post, we'll take our ruler and we'll go perpendicular. We want this to be the perpendicular component, so it can only go as long as that component. So there's our component that's perpendicular to the post. So it starts at the same point as this vector, goes perpendicular, and only goes as far as that one. So there's the perpendicular component, F perpendicular. For our parallel component, we want to start at the same point and we want to go along parallel, and we'll only go as far as this is long. So our parallel component is right here. It's a little bit hard to see, I'll draw it right here. So there's our parallel component. We know this parallel component is not going to cause any rotation at all, but this perpendicular component would cause the maximum rotation. That angle is 60 degrees. If we drew a right triangle, so we came down this far to here, so there's our 90-degree angle. This is a little bit like drawing the weight vector on an inclined plane. We have to think in those terms. If this angle is 60, this is parallel, this is perpendicular, that angle has to be 90, makes this one 30 degrees. So this one is adjacent to 30, that one's opposite 30, this one is our hypotenuse. Since our F perpendicular is adjacent to 30, we can use cosine to find that one. So F perpendicular equals F times cosine 30 degrees equals 15 newtons times cosine 30 degrees. Put that one in the calculator. 15 times cosine 30. We get 12.99 newtons, and we want to round that off to the right sig figs, 13.0 newtons. That's the perpendicular component of the force. That's the part that would cause the rotation.